In this video we continue to show how calculus is used for a function of one variable to describe the shape of the graph using the first and second derivatives. You might want to go back and look at some of the previous videos. At the very least you need to remember what we mean by a local maximum and a local minimum for a function. We also talked about what it means for a function to be increasing. As you go to the right on the graph goes up, and decreasing means that as you go to the right, the graph goes down. Now the next qualitative feature we need in describing the shape of a graph is its concavity. Here's a pretty random looking curve. This isn't a function. We don't need a function to talk about concavity. It doesn't matter which way is up, but the curve naturally breaks up into sections as determined by the concavity of the curve. Along certain sections, the curve cups one side or makes a cavity or a cave on one side, and then it flips to the other side where it becomes concave to the other direction. The arrows indicate the direction of the concavity. And the points at which the concavity flips from one side to the other are called the inflection points of the curve. If the curve were straight along some stretch, then there would be no curvature there, so no concavity. But this is describing a typical curve which is genuinely curved, and we identify intervals or stretches of the curve which are concave one way or the other. And this particular curve, as you can see, has exactly 12 inflection points. Now let's talk about functions, and then the curvature is either up or down. Here's a graph where the function is concave up, at least on the interval that's shown, is indicated by the arrows. For the graph of f to be concave up, it means, at least assuming that f prime is defined, that f prime is going to be increasing. You can see this by looking at the tangent line. As you move from left to right along the curve, the slope of the tangent line increases as you move left to right. So that means f prime is increasing, which means that f double prime is positive. F double prime is the derivative of f prime. So if f prime is increasing, then its rate of change is positive. F double prime is positive. On intervals where the graph of f is concave down, then f prime is decreasing, which means that the derivative of f prime is negative. F double prime is negative. So you can see this by looking at the slope of the tangent line as you move left to right. The tangent line tends from more positive to more negative. That's telling you that f prime is decreasing. In other words, the rate of change of f prime is negative. That is, f double prime is negative. Now let's use f prime and f double prime to study the shape of the graph of a function f. We want to look at intervals where f prime is positive or negative, intervals where f double prime is positive or negative, and then there are going to be four combinations of sign for f prime and f double prime. You can have positive positive, positive negative, negative positive, or negative negative. Depending on which combination of signs you get for f prime and f double prime, you get four different possible behaviors for the shape of the graph of f, which are increasing concave up, increasing concave down, decreasing concave up, or decreasing concave down, as I've shown you here. So you're probably going to first of all want to solve f prime equals 0 and f double prime equals 0, and then those will mark out the endpoints of intervals where the sign of f prime or f double prime changes. And I'll show you in the context of some examples how to organize this kind of information. When you do this, you have to be very careful when you're talking about f, and when you're talking about f prime, and when you're talking about f double prime. And the big pitfall that everybody makes, and the number one hurdle, is being confused about three different functions going on in your head at the same time. Don't write something ambiguous like it is positive, so it is increasing. What is it? Are you talking about f or f prime or what? You need to be very careful in just organizing clearly your information. We'll work it out how to use this in the context of examples coming up very shortly. But first of all, I want to talk about the second derivative test for local extrema. This is very popular in some books and some sources. I think it's somewhat overrated, but I can explain what I mean by that comment in just a moment. Let's say that you have a function that is defined on an open interval, and f prime and f double prime are both defined on that open interval. And you look at a point C, where f prime of C is 0, and f double prime of C is positive. Well then, you've got a horizontal tangent, but also the graph is concave up, and then that should mean that the graph has a local minimum at C. So there's a fact you can use, definitely true, and turn this upside down. So if you have a point C in the interval where f prime is 0 and f double prime is negative, then f has a local maximum at C. Once again, you've got a horizontal tangent and the graph is concave down, so that forces the graph to be have a local maximum at that point. Now here's the thing. The converse of this is not true, and so you have to be careful. There are very simple examples. Well, first of all, I should give you an example where it can be used. You can look at x squared, which has at the origin a local minimum. And you can test that by the second derivative test. Use the first derivative is 0 at the origin. Second derivative is positive at the origin. It's got a value 2. The second derivative at the origin is 2. That's positive. And that tells you the graph has a local minimum. No problem. The theorem works like a charm. But now take a pretty standard example, and this is x to the 4th. And here at the origin, you also have a local minimum. But you're not going to find it with this test, because you have a local minimum at the origin where the derivative is 0. The second derivative is not positive. It's 0. So all you really need is the previous stuff we've talked about, and that's enough. You don't need the second derivative test at all to understand what's going on in these examples. In both examples, both of these, x squared, x to the 4th, what you really care about is that for negative x values, the derivative is negative, so the graph is decreasing. For x positive, the derivative is positive, so f is increasing. And the function switches from decreasing to increasing. That means at the origin, you have a local minimum. Now this works in all cases, so you don't need any more, but you can certainly use the second derivative test if you like and when it applies. Let's apply the techniques we've talked about in the context of a couple of examples. Here is a function, a polynomial of degree 4, x to the 4th minus 6x squared minus 8x. We're asked to find intervals where the function is increasing, intervals where the function is decreasing, or concave up, or concave down, and then use this information to sketch a graph of the function, on which we'll label local maxima and minima, also inflection points. A graph like this is not intended to be drawn to scale. It's only to show that you understand the techniques and how the derivatives dictate the shape of the graph of the function f. Since I'm going to be showing you how one would try to do this by hand, I'm intentionally going to do this by hand and not use computer-generated slides for this purpose. My function is a polynomial of degree 4. I can easily take the derivatives. Now, I can find roots for these which lead to factorization. So for f prime, the roots are at 2 and -1. Now, factoring polynomials is a pre-calculus notion in principle, and you're going to have trouble with random polynomials, but these are not just generic polynomials. These are hand-picked so that they factor nicely, which means you can find the roots nicely. So you'll have to do that on your own time. I can't take time to go through that here. And f prime is 0 at -1 and at 2. F double prime is 0 at -1 and 1. So those are the important points I need to consider. I'm going to mark them out on an x-axis. This is not our graph yet. This is just rough work to guide us toward the shape of the graph. So if you like, I'm making a one-dimensional description of the function where I just look at the values along the x-axis as to their sign, as the 0, positive or negative. So I'm going to talk about f prime, and f double prime separately. So f prime is 0 here and here. F double prime is 0 here and here. And in between, I just mark out whether each of these is positive or negative. For example, between plus and minus 1, I'm going to get a negative times positive. It's negative. And to the left of -1, both of these are negative. Their product is positive. For x bigger than 1, they're both positive. For f prime, for x bigger than 2, positive times positive. Between -1 and 2, I have negative times positive. That makes this negative. And to the left of -1, I have negative times positive is again negative. Now, on each of these intervals, from -infinity to -1, I see from the sign of f prime is negative and f double prime is positive. That means that f itself is decreasing concave up. From -1 to 1, both f prime and f double prime are negative, so f itself is decreasing concave down. Between 1 and 2, f prime is negative and f double prime is positive. That means f is concave up and decreasing. From 2 to infinity, f prime and f double prime are both positive. That means f is increasing and concave up. Now, the table I'm showing you here is just rough work. This doesn't answer the problem. The problem needs an explanation in words. And so let me start by giving the behavior of f on intervals. F is, first of all, decreasing on the interval -infinity to 2. Now, you can see here, first of all, that f is decreasing from -infinity to -1, and it's decreasing again from -1 to 2, which means overall f is decreasing on this entire interval. You will be fine to list those intervals separately, but I'm putting them together, which is simpler and more natural. You could also, by the way, make this a closed interval, and that would also be correct. You could make it closed at 2. F is also increasing on the interval from 2 to infinity. That's because f prime is positive there. For concavity, f is concave up. Wherever f double prime is positive, that is on the interval -infinity to -1, and on the interval 1 to infinity. And f is concave down on the interval -1 to 1. Don't try to put these intervals together with union or anything. It would not even be correct to do that. Just leave them the way they are. Now I'm going to sketch a graph. This is not going to be to scale. In fact, really be. At least they cannot choose the same x and y scale if you want to make it clear here. But I'm going to plot the points that are relevant to us. And when I plug in -1, 1, and 2, first of all, 2 is going to give us something really low, 2 minus 24. And so that means that the scale for y is going to have to be more compressed. That's okay. If I put in like 1, I'm going to get a negative 13. That would be about here. And that means when I put in a negative 1 and I get a value of 3, if I want to keep the scale, roughly scale, then I'll put it here. Now I'm also going to point out that the curve goes through the origin. F of 0 is 0, so that helps me. Why not put that in as well? To the left of negative 1, the function has this shape, decreasing concave up. Between minus 1 and 1, f is decreasing concave down. It also has to go through this point. From 1 to 2, f is decreasing concave up. Make the graph show that by the way I draw it. And then after 2, the graph is increasing concave up. And you don't know exactly where this crosses because that would be finding the roots of the other cubic factor of this polynomial. You can actually check numerically that that's somewhere between 2 and 3. If I put 3, it's the x-intercept here, the root is not exactly at 3, it's a little bit less than 3. But that's not going to worry us in our qualitative graph. Notice here at the point minus 1, the derivative is 0, so we have a horizontal tangent. That's a critical point. So this is not a local extremum. It is, in fact, an inflection point because the curve changes concavity there. It goes from concave up to concave down. There's another change in concavity at 1 minus 13, where the graph changes from concave down to concave up. So f has inflection points. Minus 1, 3, and 1 minus 13. This inflection point has a horizontal tangent. This one does not. Now at 2 we have another critical point, and this one is a local minimum. Because the curve is decreasing on this side and increasing on this side. That's enough to check that there's a local minimum. You can also check by the second derivative test, which in this case the second derivative is positive. That tells you this is a local minimum. Local minimum point at 2, and the value there is minus 24. Now, this is also a global minimum. I know I didn't list this as one of the things you had to answer, but we might as well point it out here. It's the absolute minimum. Because the function is decreasing up to this point and increasing after that point. So this is a good example to complement what we did before with closed intervals. If you have a continuous function on a closed interval, you know there's going to be an absolute maximum and minimum. If you don't have a closed interval for the domain, if it's not just an interval a, b, then how do you check that something is an absolute maximum or minimum? Well, in this case, it's by the fact that the function is decreasing up to here and then increasing after there. That is exactly what you need to say that this is the absolute minimum, and there's only one. F has no local or absolute maximum. No absolute maximum because on the tails, on the ends, both ends, the curve goes to plus infinity by taking the limit of this polynomial. And there are not even any local maxima because we looked at all the critical points. One of them was an inflection point, the other was a local minimum. So there's not even a local maximum. Second example, like the first except this time not a polynomial. The function f of x is x e to the x. Now this function is not a polynomial, no problem. We take the derivative using the product rule. Factor. Derivative again by the product rule. The exponential is always positive, but the sign of each of these functions you find by the other factor, the polynomial factor, and f prime is 0 at -1, f double prime is 0 at -2. We mark out those 2 points on an x-axis, just a one-dimensional description of the function. What's going on? We list f, f prime, and f double prime separately, noting where they're 0 and where they're positive or negative. F prime is 0 here, f double prime is 0 here. For x bigger than -1, f prime is positive. For x less than -1, f prime is negative. And for x bigger than -2, everything here is positive. For x less than -2, you have negative times positive is negative. And on each of these intervals, first of all from -infinity to -2, the function is decreasing concave down. Between -2 and -1, f prime negative, f double prime positive means that f is decreasing concave up. And beyond -1, both f prime and f double prime are positive, so f is increasing concave up. So we can sketch a graph based on all this information. Let's move our y-axis a bit more to the right. And I'll mark out the points here. What happens at those 2 points? You have -1 over e, and -2 over e squared. And this point is a little lower than this one. And by the way, the graph also goes through the origin, since f of 0 is 0, so I'll put in that point for free. Okay, and now, to the right of this point, f is increasing concave up. Rises somewhat steeply. Between -2 and -1, f is decreasing concave up. And between -infinity and -2, the function is decreasing concave down. So I'll try to suggest that by the shape of what I'm drawing. F is decreasing on -infinity, -1, increasing on -1 infinity, concave down on -infinity, -2, and concave up on -2 infinity. And we've indicated that already by the sign of f prime and f double prime, but we need to say it in words because this is considered rough work. Everybody has a slightly different way of depicting this notation. As long as you organize it well, it makes sense to you. This is your scratch work. This is where you are actually answering the problem. F has an inflection point. There's only one. It's at -2 over e squared, because that's where the concavity changes from concave down to concave up. No other points where that happens. And a local minimum point at -1. The value there is -1 over e. And since it's the only local minimum, that is the absolute minimum. So you notice here that the function decreases up to this point and increases after that. So that tells you that this is an absolute minimum. The absolute minimum is the only place where it happens. You can use the second derivative test here to check for this being a local minimum. So you look at the second derivative at -1, that's a positive value, so that tells you the shape here is concave up, which is telling you you have a local minimum, second derivative test. But since you already have everything you need without the second derivative test, I just mention it briefly in passing. And there's no absolute maximum, because look here, the curve goes up with a limit of plus infinity as x goes to infinity. No, there's not even any local maximum. No local or absolute maximum. Now I will mention also, I've mentioned the limit on this side is plus infinity. You do have the limit on this side is plus infinity on this side. The limit is 0, which is saying that the x-axis is a horizontal asymptote. But that may not be something that you find easy to get right at this point in the course. I can do it. I have done it in my class with the tools available using the mean value theorem to see that on this side you have a limit of 0 so that you have a horizontal asymptote. Once we get to L'Hopital's rule, we can make quick work of that, so I'll just postpone a full discussion of that until we get to the L'Hopital's rule.